All right, everyone. Hello and welcome to Motor Starting 101. If this is your first time joining us, welcome. And if you've been on other engineering webinars in the past, welcome back. So some topics we're going to cover today include converting motor LRA into starting kVA and kW, impact of alternator size and subtransient reactance, engine and alternator transient performance interaction, voltage dip versus recovery voltage, and methods to reduce motor LRA. A little bit of housekeeping. There's a question box in your side GoToWebinar panel. If you have any questions throughout the duration of the webinar, feel free to type those in there and we'll answer them at the end during our live Q&A session. Get ready for polls. We do have a couple throughout. Once we ask the question and launch it, it'll pop up on your screen. Click the answer that you want to choose and hit submit to send those responses in. When you leave the webinar, you'll be getting an exit survey. It'll automatically prompt you to take that. If you can take a minute to fill those answers in, that's much appreciated. We use those to keep our content up here. And then last item is letting you know that you'll get an email tomorrow with a link to request your free in-person training for those continuing education credits, as well as a link to the recording of this email. My name is Laura Unger, Industrial Manager here at Generac, and at this point I will turn it over to our presenter, Michael Kirkner.
Thank you, Laura. Appreciate that. So let's chat about motor starting. We find with generators, one of the interesting aspects of applying a generator to a load is when we start a large motor. And when we start a large motor, it actually applies a transient condition to both the engine and the alternator on the genset. The alternator controls our voltage dip and our engine controls our frequency dip. So when we start a motor, an electric motor, we draw about 6 times running current or 6 times running kVA. And we have to hold that current until the motor accelerates. Typically, a motor on a high torque load may take 2 or 3 seconds to come up to full speed. So when we're trying to do our calculations, it's much more convenient to convert things into SKVA. A lot of rules of thumbs work very easily once we're talking kVA. If we're talking amps, every time you change your voltage, you lose a total sense of relevance for the magnitude of the number. So first thing we like to do is take the LRA that's on the nameplate and convert it into a kVA. And that equation is right there in front of you. Volts times amps, square root of 3 for 3-phase, and divide by 1,000. Once we have that information, we can see I plugged in a 750 locked rotor amps, and that led to 623 SKVA, which, because I kind of know my rules of thumb, that's about a 100 horsepower motor. The other way we can calculate an SKVA, a starting kVA, is to use the NEMA starting code. So sometimes they'll list the LRA. The other thing we could do is look for the NEMA starting code. Code G motors are most common, so we would multiply the horsepower by the factors you see in the table. The typical number we use for rule of thumb sort of sizing is 6, kind of midway in code G. So if I had a 100 horsepower motor, times 6 is 600 start kVA. So that is going to be the impact on the alternator. So typically this is nameplate data. Sometimes we see customers confuse NEMA design codes for starting codes. I don't think you're ever going to find a B, C, or D starting code in the actual marketplace. You will see code F and G and higher, but you won't see those low letters within the market. So you're really looking for that NEMA starting code or the locked rotor amps to get you to an SKVA. High efficiency motors, higher starting currents. International motors, IEC motors, European motors, higher starting currents. Which leads us to our very first polling question.
And the question is, when sizing a genset for starting a motor, please select one of the options: size based on altitude, size based on voltage dip, size based on recovery voltage, or uncertain. Give everyone a few more seconds to get those responses in. Just click the bubble on your screen and then submit. All right. And we had a clear winner, size based on voltage dip.
Yeah, 80% of you said based on voltage dip. Only 6% mentioned recovery voltage, which actually is going to lead us to something we want to chat about, in that if we take an alternator and we apply a small motor, we'll get a small voltage dip. So for instance, in these series of lines you see on the page in front of you, let's call line A a 10% voltage dip, relatively small motor on a genset. And then we take the small motor and put it away and get a little bigger motor. We get a little deeper voltage dip. And we keep doing that process until we kind of push the genset to its absolute limit, which is line B, which is a 35% voltage dip. Now, one of the things I do want to point out is there is one competitor in the marketplace that specs their genset performance on their spec sheets, not based on voltage dip, but based on recovery voltage. That is not what you all typically said you want to do. You said you want a size based on voltage dip, not recovery voltage. So it's a little bit confusing when one competitor in the market will use recovery voltage as the SKVA value. It does create a higher SKVA value than others in the industry because you're really pushing the alternator outside of its normal workable range. We tend to limit 35% voltage dip as the max because that's the maximum a NEMA motor starter can handle. If you start dipping voltage more than that, the motor starter drops out. The other reason we don't like to push way beyond the 35% voltage dip is once you start getting to the point where the alternator is not recovering anymore, you're only recovering to 90%, you're really at the limit of the alternator. You're really starting to squash it. That magnetic field is being compressed so much by the large SKVA that you're not going to get much of a recovery. So if you inadvertently have a little more than what you estimate, it's really going to recover quite poorly. So why does the voltage dip on an alternator? When we apply the locked rotor amps, when we close the contactor and the motor draws LRA, that current flows through the windings of the alternator. Think of the windings of the alternator as a tight spot. And as that current flows through that tight spot, that impedance, source impedance, we're going to get a voltage dip across it. So basically, the voltage dip we experience on a genset is a function of two parameters: the amount of current, the LRA of the motor, and the subtransient reactance of the alternator. So the bigger the alternator, the lower the effective subtransient reactance and the less voltage dip. So one of the things we're going to discuss is we at times will upsize the alternator, put a bigger alternator on a given engine because we're trying to drive that subtransient reactance down to get less voltage dip. And here's an example of that. Taking a 50 horsepower motor, 300 SKVA, and applying it to different size gensets, we can see that as we try to push that voltage dip lower and lower and lower, the size of the alternator has to go up quite significantly. So one of the things we're looking at from an application standpoint is either using a big alternator to keep voltage dips in check with what the rest of the loads can handle, or maybe put something like a soft start or drive on your bigger motors. So from a genset standpoint, we have two components. We have the alternator, which controls my voltage stiffness, and we have the engine, which controls the frequency stiffness of the genset. So when we're starting a large motor, we're going to actually apply some kilowatts up against that engine, and how that engine responds is a function of a few different things. It's fuel type, the displacement of the engine, the type of technology in play. So one of the things, if you're looking at calculating frequency dips, you really want to use a sizing program from the OEM of the genset in order to estimate the frequency and voltage dips that you're going to see. Which leads us to our next polling question.
Polling question number 2. When converting from the electric motor's SKVA to the SKW, impact on the genset's engine, either multiply the SKVA times 0.3, multiply the SKVA times 0.85, multiply the SKVA by 2, or uncertain. I see responses coming in. We'll give you a few more seconds. All right.
So we actually got quite a few on this one. A lot of you said, 60% of you said multiply by 0.85. 0.85 is the power factor of a motor when it's running. When a motor's running, we have a little bit of kVAR on top, but there's a lot of kilowatts that are flowing into that motor. So in the starting phase of a motor, there's very little mechanical work going on. So the end result is we're rushing all of these amps into the motor, and most of those amps are kVAR. So it's actually a very low power factor event when we're starting. So multiplying the start kVA by 0.3, which is starting power factor, will give us the start kilowatts. So just coming back from a definition standpoint, power factor is just a ratio of kilowatts to kVA. We can put little S's in front of everything to convert this from a running condition to a starting condition. So if I want to calculate my starting kilowatts, I need to plug in the starting power factor. And motors start at a low power factor, around 0.3. It's actually a range of power factors, but it's actually fairly low, around 0.3. So for a 100 horsepower motor, we're going to draw 600 SKVA, which translates into about 180 kilowatt hit on the engine. So we will see a frequency dip on the engine. If you want a rule of thumb, just take your motor horsepower times 2. It's a little fat, that rule of thumb, but it's, you know, a quick and easy number to remember. So if I want to start a 100 horsepower motor, I need about 200 kilowatts of available engine capacity. How much we're going to get for frequency dip, again, changes a little bit depending on, you know, if it's a diesel or gas engine and some of the technologies that are involved. Most loads don't care too much about frequency dips. Most loads are very voltage dip sensitive. So what we find is a lot of our more sensitive loads want to limit voltage dips to about 15%, but the limits on frequency dip generally aren't in play. The only exception to that is older UPS technology called line interactive technology. So some rules of thumb, you know, we mentioned SKVA is about horsepower times 6. From a kVA running standpoint, an electric motor runs at about its horsepower. A 100 horsepower motor will run at about 100 kVA. That's another nice, really handy rule of thumb. So for all of you that wanted to plug in 0.85 before, you weren't wrong. It's just we have to use that in the running phase, not the starting phase. So horsepower times 0.85 is the running kilowatts that a motor is going to draw. So a 100 horsepower motor runs at about 85 kilowatts. Those rules of thumb work really fairly well. I use them a lot. It's a way I do quality control. When somebody gives me some information, if the numbers don't seem to jive, I start raising my hand. And I would encourage you all to use some of that same rule of thumb. If somebody gives you 2 different numbers, running and starting, and the numbers don't seem to mesh, it's a way to ask, hey, did we get a bad number? The only time those rule of thumbs kind of skew way off would be submersible well pumps, like in freshwater municipal sites for, pumping water out of the ground for a water tower. Those pumps are put way down the borehole and they're long and skinny, so they draw very high starting currents. So if we were to look at a application and we had 3 motors, let's just assume it's at a pump station. So we got a 50, a 100, and a 200. I discovered over time that a lot of manufacturers out there will tell you, well, you always start the biggest motor first. That's true if you're trying to produce the smallest genset. So if you start the biggest motor first, that means you have no load on the generator when you're starting the biggest load. So you have the most available capacity. So you will get the smallest generator. What they're not telling you is that doesn't really work for most real-world situations. In most real-world situations, motors cycle. That means they start and they stop all the time. And very rarely do you shut everything off to restart the big motor. You keep the things running that are running, and when the big motor kicks back in, it starts last. So keep that in mind. A lot of people will approach you and say, well, start the biggest motor first. Yes, you get the smallest generator doing that. But what they're not telling you is that doesn't match what happens in most real-world situations. Most real-world situations, motors cycle. That means that big motor is going to shut off, and at some point, it's going to want to restart. So one of the things we can do to help the size of the genset when we're starting big motors is we can limit the LRA, locked rotor amps. One of the devices that's used quite a bit today to do that is called a soft starter. And what soft starters do is they limit how much voltage the motor sees, and it does that by gating the sine wave and only allowing a piece of the sine wave to come through. So what they can do is start off with just a very small piece of the sine wave, very low voltage, and ramp voltage up until you get the complete sine wave being applied to the motor. By doing that, we can create a non-transient condition on the genset, because we just see a little bit of load at first, and then it ramps voltage up over a few second period. And as we ramp the voltage up, the motor starts accelerating and the speed picks up, and the genset doesn't see a big transient condition. That's called a voltage ramp, and that assumes a relatively low breakaway voltage. So if I start off at, let's say, 20% voltage and I ramp up until I hit my current limit setting, and then from my current limit setting just keep pushing the voltage a little bit until we get the motor up to speed, creates a very easy application for a genset. There are some soft starters in the market that don't give you that option. They're just set up to go to current limit. So it's like breaking away at a much higher voltage, maybe 0.4 volts, maybe 40% or 50% voltage. Well, if I break away with a lot of voltage, 40 or 50%, I will be creating a transient on my genset, and we're going to see a voltage dip, and we're back into the same problems we saw before. So anytime we can use a good industrial soft starter, always dial in that voltage ramp up. Start low and ramp up, and you won't have a problem on your generator in terms of transients. Just to show you the difference between a voltage step approach and a voltage ramp, if I break away to a 300%, if I break away to a 300% current limit setting, for this particular example, I needed a 250 kW alternator to hold a 20% voltage dip, and that was on a 100 horsepower motor. Instead, if I do a voltage ramp, break away at a very low voltage and ramp up, now I can get away with a much smaller 130 kilowatt alternator because I'm not making that big step on the alternator. Just some final thoughts on soft starters. One of the things they don't do a great job of is publish their voltage dip tolerances from the soft starter manufacturers. We find that most of them seem to work fine with a 20% voltage dip, which seems to work for most general applications. if I'm tying a whole building to the application, I might want to limit my voltage dip more like 15%. Or if you had a fire pump in play, it's a 15% voltage dip limit by code. Use voltage ramping anytime you can. That's a nice feature. It's typical for most industrial soft starts. Unfortunately, the hydraulic elevator market uses soft starters quite a bit, and that particular market, the soft starters that are most common in that market don't give you that functionality. So they break away on a straight up step up to a current limit start. So they're kind of a difficult application. They require a much bigger generator on a hydraulic elevator than you may anticipate, because the soft start's not really helping you all that much. Anytime you can sequence your soft starters, a soft starter will produce harmonics during the starting phase, but once the soft starter is fully up to speed, the harmonics go away. So anytime you can sequence them, it just keeps some of the harmonics down while they're starting up. The last thing I want to mention is we're seeing the marketplace, because of the cost savings involved, implement two-phase soft starters. So my little diagram that I had before showed switching devices on the A, B, and C phase. Well, obviously they can save some cost if they only switch on 2 of the 3 phases. That does work from a soft starter standpoint. However, the uncontrolled leg will draw 30% higher current than the other legs. That just means that we're going to have a higher SKVA than predicted for that leg. So one of the things you can do is we're looking to add that as a feature within our sizing program, to add two-phase soft starter as just an option that you can select. But in the interim, just simply bump your SKVA value up by 30%. It'll correct for the soft starter only using 2 phases. The last thing I want to touch on is Y delta starters, which are quite common in fire pump applications. A lot of fire pumps suppliers and customers hold on to the old Y delta starters instead of using soft starters and drives. And Y deltas do create a unique situation. Y deltas basically reduce voltage on the motor. So you start in a Y connection and then you switch over to a delta connection for running. What that means is the motor windings are getting less voltage during starting. How much less voltage? Well, they're only getting 57% voltage, which means your current drops way down, but your torque also drops down appropriately. And the reason Y deltas and soft starts were used on fire pumps is mechanically they're trying to soften the hit from when that motor starts. They don't want to jam the coupling and create like a water hammer effect with the pump. They want to soften that, so they want the torque to be reduced. Which leads us to our last question.
And the question is, when starting a fire pump on a Y delta starter, SKVA is reduced by 0.33 initially. SKVA will spike before reaching full speed. Both of those options, or uncertain. So go ahead and put your responses in. Few more seconds here. All right. And it looks like both A and B won, with 51% choosing that option.
Yeah, that's actually what we're going to see. We're going to start off initially with a pretty low SKVA. And what we're going to find is we're going to run out of torque, and that's going to create an early transition, and it's going to cause a spike. So Y delta starters only give you 33% of locked rotor torque. So think of it this way: locked rotor torque on a motor is normally about 180%. So if I'm only getting 0.33 of 180, I'm only getting 60% of rated torque. At some point, that fire pump is turning faster and faster and loading up, and I just run out of torque. So when using a Y delta starter, you normally try to set that transition time as far out as you can, So you let the motor push and push and push 4, 5, 6 seconds, so you get as high up in speed as you can, and then transition over. And you will get a spike at that transition point. But we're trying to get as close to rated speed as we can to minimize that spike. So one of the things Generac sizing software does, it takes an estimate of where we think that spike is going to be. So the sizing program that we have, it's Power Design Pro. It's on our public website. So if anybody wants to use it, just simply Google Generac Power Design Pro. It'll be the first option that comes up. And within our sizing software, we give the users the ability to select the load characteristic. And for a fire pump, we default to the middle one there called low torque at start. And if you notice, this is a 100 horsepower motor, and we know that a 100 horsepower motor is going to take 600 SKVA to start. Now, when we apply a Y delta starter, that number can be all the way down at 0.33 of that, or right around 200 SKVA. But that doesn't give us what's actually going to happen on the fire pump. It's going to start with that low number, but somewhere around 70, 75% speed, it's going to switch from low voltage start to full voltage run. It's going to spike up. When it spikes up, we need to model what that SKVA hit is, because that's actually going to create the worst voltage dip for the application. And if the voltage dip's more than 15%, the fire pump controller kicks off and everybody's unhappy. So this is something that Power Design Pro does that we haven't seen elsewhere in the market. It actually tries to protect you from that misapplication. A lot of the competitors' sizing programs will just plug that in as it was an unloaded motor at start.
And that leads us to our questions. I know I had a lot come in here, so we're gonna start answering those here. First question is, some salespeople use 30% VD instead of 35%. Is this acceptable to Generac?
Yeah, I mean, when you're using a NEMA motor starter, you know, most engineers will design anywhere between 25 and 35% voltage dip. Any of those is quite fine. Those voltage dips work quite well if you just have a few pump motors. As soon as you integrate a generator into an entire building, let's say a whole facility, or I have some VFDs in the mix, then all of a sudden you need to start dialing your voltage dip down to about 15%, because there's a lot of loads out there that aren't going to be happy with a 25 or 30% voltage dip.
With medium-sized motors on VFDs, should voltage dip be held to less than 35% to avoid fault trips on the drive?
Yeah, so VFDs actually are very easy from an application of a transient. They have a different problem, usually harmonics. VFDs ramp voltage and frequency up simultaneously, so the motor always has full rated torque. So the motor can start off with a very low input and ramp itself up with full rated torque. But that means because they start with the frequency and the voltage on the output of the drive so low, there's very little load being put on the generator, and it just simply sees a ramping of load. So you won't see voltage dip problems when you have a VFD. What you will see if the VFD isn't filtered or IGBT, you're going to see a lot of harmonic problems. So you always want to use a good VFD that has a low harmonic front end on it.
Are there any special considerations for motor starting when the motor is an elevator connected to the generator?
So there is two types of elevator applications, cable and hydraulic. A cable elevator is basically a VFD that has regenerative capabilities, because when the elevator car comes down, the drive has to hold back or brake. That's called a regenerative drive, and there's two ways to manage that. One way is with a braking resistor built into the drive, kind of older school technology. What we see more today in the market is a 4-quadrant drive that will push power back to the source. In that scenario, we need that power to be burnt away or dissipated by other loads in the system. So for a typical 40 horsepower elevator motor, figure about 32 kilowatts is going to be pushed back at the genset. we need that power to be burnt away because the generators aren't great brakes. They typically will only break about 10% of their rating. So if I have a 100 kW generator at about 10 kilowatts of reverse power, the generator isn't holding back anything anymore. So we usually look to have that regenerative power burnt away by other connected load. And if we can't get any other connected load, we typically recommend a load bank be connected.
All right, I know we're at our 30 minutes here. So for those of you who do have to leave, again, reminder that there will be an exit survey as you leave. If you can go ahead and put your responses in there. And then tomorrow you'll be getting an email sent to you with the recording link of this webinar. It'll be a video. We don't send out the slides. So if you need something to reference, you can always go back and look at that. And there's also going to be a link to request a free in-person PDSS class. Those are for continuing education credits brought right to your door. We're going to stay on to answer the questions that came in, but one more note, if you have any questions that come up in the future after this webinar, you can always email those to indweb@generac.com and we'll make sure to get those to the appropriate expert to get them answered for you. There is one question on here, where can we find Generac's generator sizing software? You can find that online at generac.com/industrial. That's our site. It is located there in our resources, or you can just do a quick Google search of Power Design Pro and that'll take you to the right link also. Another question for you here, Mike. Can you address the use of VFD with generators? Should we identify 6 pulse, 18 pulse, 24 pulse, or IGBT, etc.?
Yeah, I mean, you're trying to get the harmonic distortion down under 12%. That can be done with a filtered 6 pulse, it can be done with a 12 pulse, or it can be done with IGBT input. So anything that brings your harmonic current distortion under 12% usually takes care of the problem. So any of those options will work for you.
When you discussed Y delta starters, that was for closed transition Y delta starters, correct?
Within our sizing program, we have both open and closed. The closed will give a little bit lower result than the open transition. The open transition spike will be a little larger. So we kind of try to model both. And we're assuming that that motor is going to be allowed to work for, 5, 6, 7 seconds to get as close to rated speed as it can before it transitions over.
Please discuss the use of active front end VFDs on generators. What is max % of total load that can be AFE VFDs?
Yeah, so an active front end kind of implies regenerative power capabilities similar to the elevator discussions we were having. So usually a generator can only break about 10% of its rating. So 100 kW generator is usually about 10 kilowatts of reverse power. So anytime you have active power factor front ends that you're going to regenerate with, you're limited on that. We would normally recommend other connected loads.
How does a regenerative drive on an elevator affect the performance of the generator?
Normally the performance is unaffected unless you push too much power back to the generator, at which point you're going to get an overspeed shutdown.
Do part winding starters offer similar starting characteristics as delta Y starters?
Yeah, they each have a little bit different characteristic. Yeah, but a part winding is going to have a similar sort of problem. The numbers are a little bit different. It depends on where the winding's tapped at. So kind of a similar problem. Depending on how much voltage you apply, the problem can be more or less in terms of its impact relative to transitioning early. So if you use maybe like a 65 or 70% part winding, you should have a lot more torque maybe than, less of the motor winding. But similar situations in play.
What is generally the safest voltage dip to prevent contactors from shattering?
For NEMA contactors, anything under 35%. I would normally design with a little extra headroom in there, probably in the 25 to 30% range. when you're looking at it holistically, sometimes the best solution is just to look at the biggest motor and say, let's take the biggest motor out of the equation and either put a drive or a soft start that does voltage ramping, and let's fix the problem at the source instead of maybe trying to kill it with generator size.
Is there an oversizing rule of thumb for standard 6-pulse front-end VFDs?
For standard 6-pulse front-end VFDs, 480-volt machines, you probably need about 2.5 times on the alternator. So if you have 100 kVA UPS or 100 kVA nonlinear load with 6-pulse unfiltered, you need about 250 kW on your alternator just to keep the voltage distortion in check.
Okay, I like this question. Can you have a future webinar showing how to fill out and apply the Generac generator sizing software? We already have one, Robert. So if you go to our website, generac.com/industrial, in the webinar tab, all of our webinars are located there on demand, and you can view, I think we've got one or two where we show you how to use the Power Design Pro software. Next question, will a capacitor bank help mitigate voltage drop?
It's tricky because generators don't like leading power factor either. So when the motor's not currently starting, you're going to be left with all that capacitance, and leading power factor causes voltage instability and over voltage shutdown. So capacitive connection theoretically could be put in play, but it would have to be just implemented during the start phase of the motor. And there's not a good implementation of that out there in terms of to try to provide some kVAR right at the generator. I know there are some very small, like air conditioning motors that have quote unquote hard start kits, which is nothing but a capacitor that they kind of hook into the start winding. But when we deal with 3-phase motors, we don't have start windings. We just have the whole winding set.
What can you tell us about generator sizing where ISO 8528 G3 compliance is a requirement?
The ISO requirements, you need to be a little careful because unless you're really up on your G1, 2, and 3 compliance within that ISO standard, it can be a little challenging. That standard has some tables in there based on, if I remember right, BMEP of the engine that you can make some pretty significant adjustments. So it isn't as straightforward as defining a specific voltage dip, because what happens is those standards actually say you get to derate what you're calling your input transient based on the BMEP of the engine. So unless you're really familiar with that standard, I would not hold my hat and say I spec G3 and that somehow is going to mean something to the market. If you're looking at making everybody compete on an even footing, just spec the voltage dip that you're expecting and spec how much SKVA you're expecting. So if you know the biggest motor, input that SKVA and what voltage dip you want to hold.
You mentioned VFDs with managed harmonics have a smooth ramp up in SKVA and RKVA. Does this mean that they have a lower starting impact compared to soft starters?
Yes, in essence they do. A drive will allow the motor to have full torque at any speed because it ramps its output voltage and frequency. A soft starter only ramps output voltage. It's still putting out 60 hertz. As a result, a soft starter works more like a traditional electromechanical reduced voltage starting device. So as long as you start and use a voltage ramp characteristic, you're going to have a couple second period maybe where you're really trying to generate enough torque to get it accelerating and just keep ramping up. The problem we have is so many people bring soft starters to site and their default set to just do a current limit start, no voltage ramp. And at the end of the day, now you're making a pretty significant transient on the genset. And until you get the right technicians out there to adjust the soft starter, there's usually a little angst in the marketplace. Some of the low-end soft starts may not give you the ability to ramp voltage. So that's something you should always be thinking about. Anytime you're using soft starts and you want to try to match it to a generator, If it's going on the bigger motors, I'm not worried about the small motors, but if it's going on the big motors, always make sure it's a good industrial soft start that can do a nice voltage ramp for you.
All right, and our last question today is, how does a PF other than the gen rating affect the alternator and engine?
The PF being the power factor. So power factor of the load, generators are rated to run anywhere from 0.8 lagging up to unity. They're not necessarily rated for leading power factor. So our biggest problem tends to be on the leading side of things. So that's usually the only thing from a power factor discussion you need to be aware of. Don't use leading power factor loads, which would be power factor correction caps, for instance, within your power system. Or it could be a lot of VFDs with harmonic filters that are running very lightly loaded. That could be another situation where you run into a leading power factor condition. Generally, we don't run into problems with low power factor. Other than the motor starting discussion we're just having. That becomes part of the generator sizing. During that starting phase, we get a lot of LRA, a lot of hit on the alternator, and we need to plan for that voltage dip.
All right, Mike, I want to thank you so much for being here today. If you have any other questions, you can always send them in to indweb@generac.com, and we'll make sure to get those answered for you. Thank you for joining us today, and have a great rest of your afternoon.